All right, we'll begin, and happy Monday, everybody. Welcome to week 4. I know it's now midterm season, so I hope you guys are doing okay. Anyway, any questions before I get started? I'm still writing the exam, but I'm using what I told you on Friday as a guideline for myself to write the exam. So I don't have much to add between kind of what I talked about the midterm on Friday and today. Yes.
So we don't have to write any R.
No R code. No R code. No neural networks. The topics we covered. There, yeah, so it's, the class is a lot more mathy than like 102A. There's still a lot of code involved. Pretty much everything we're learning is so we can code things up eventually and get these things to run on the computer, but there's now a lot of math behind what we're coding up. So, okay. Any other questions? We're good. All right. Then we'll continue on talking about backpropagation in neural networks. So this is kind of where this is the example neural network that we're starting. This is probably the simplest version of a neural network that we can still that kind of maintains, the different pieces of a neural network, and we can, and I think it's complex enough to that we can see the math, and then and this will just generalize to kind of higher dimensionality. Okay, so our neural network, we've got our X input has 2 columns. Okay, we've got an X1 and an X2, 2 inputs. We multiply that by some weight matrix W, which is 2 by 3, and that outputs, an n by 3 matrix Z, which we then apply an activation function to turn everything into an n by 3 matrix A. We multiply A by another set of weights, a 3 by 1 matrix, which will turn that into an n by 1, and then we pass that through an activation function, and we get n by 1 scores for y hat. Okay, and again, this is what we're using as our loss function. We're just using kind of the difference between the actual and what our neural network predicted, the y hats. We take that difference and we square it, and for simplicity, we got rid of the 1 over n. And then we just throw in another factor of 1/2. I know I saw on Campus Wire there's a lot of questions about whether we have to keep in a 1 over n or 2 over n constant and things like that. And why didn't I include some of these things in some of the lecture notes and stuff? So in the homework, I think I gave some like sample answers and things like that. And I think to kind of get your answers to line up with the sample answers I have, you can leave in the 2 over n constant, whereas, but at the end of the day, whether, at least for some of these loss functions, whether you're trying to optimize the sum of squared errors or the mean squared error, and that's the difference between the 1 over n factor and not, the values that optimize the sum of squared error will be the same values that optimize the mean squared error. So in a lot of these things, whichever function you choose to optimize will result in the same answers. But if you want your numbers to kind of line up with the numbers that I put in the homework as kind of examples, keep in that factor. Okay, so we have 2 gradients to calculate here for the loss function. Okay, we've got dj with respect to our first weight matrix and dj with respect to our second weight matrix, and this all kind of involves working backwards via the chain rule. And so we're first do the loss function with respect to the second weight matrix. And because J itself is a scalar output, whenever you take a partial derivative with respect to a vector or matrix, it's going to have the same dimensions as the vector or matrix itself. And so anyway, on Friday we worked through the steps to get dj with respect to W2, and we arrived here, okay? And we said, and so it involved some rearranging of terms in order for the dimensions to line up. We were able to get rid of the summation sign because for a lot of these things, as you're calculating the derivatives and gradients and things like that, these partial derivatives, personally, I think it makes sense to work with one observation in the beginning, okay? Just say you're gonna kind of look at one row in X, which is one observation, and you feed it through the network and you get kind of one output at the end, and work for that. And then once you get it working, or once it kind of makes sense for one observation, then you can generalize it to n observations. And so when we did that, for one observation, this is just a scalar value, but when you generalize to n observations, then we realize we need to use element-wise multiplication, and then the A matrix needs to be transposed so that the matrix multiplication lines up. Okay, that's kind of the important thing when dealing with matrices, is you always kind of have to make sure your matrix dimensions line up, and this is often kind of the hardest part and most frustrating thing, especially if you don't go through the work of making sure your dimensions line up. When you try to code it up in whatever language you're using, you're going to get all sorts of dimension mismatch errors, and so it's a lot of work writing the dimensions underneath everything, but it helps out. Okay, so anyway, this is where we left off, and then we called this thing this minus y, negative of y minus y hat multiplied by f prime of z3. We called that delta 3, and so we have A2 transpose delta 3, okay? And I'm using this so that my notation and labels of matrices align with the notation that appears in the Welch Labs videos, which I think are good, although he kind of blasts through the back propagation video in just a couple of minutes, and I guess I'm belaboring this stuff a little bit here. Okay, so anyway, now we want to get the loss function with respect to the first weight matrix, and the beginning parts, at least up to here, are the same as these steps with respect to W2. And I don't know if I need to go through all of this again, but we take the partial, J is this loss function, we take the partial with respect to W1, and when we do that, the 2 comes down and cancels out with the 1/2, and via chain rule, we multiply it by -1, and we have dy hat with respect to W1. Again, we don't have any derivative with respect to y, because y is a fixed constant in our data, and our data is fixed, and so does not change with respect to W1, our first weight matrix. Okay, and then we split up this partial into y hat with respect to Zn, and Zn with respect to W1, and y hat with respect to Zn is the sigmoid prime, because what we've done is we've passed Zn3 through our activation function to get our y hat sub n. Okay, so this is just for observation n, and this is what we have so far, and so this is where we are now. Okay, and so now we want the partial derivative of observation n's Z3 value with respect to W1, okay? We said this is, so far this is a scalar, and so we split this part into Z with respect to A and A sub n, and then the partial of A sub n with respect to W1, okay? And so in order to get the partial of this scalar Zn with respect to A sub n, we take a look at how we got this, and we can see that if we take the gradient or derivative, partial derivative of this with respect to an, it's going to be W2. It's just a product of these two things, but we're going to have to transpose it so that the dimensions align, right? Because if we take the gradient of z with respect to an, the result needs to be 1 by 3. And so if I do W2, that's 3 by 1, so I need to transpose that to turn it into a 1 by 3. Okay. And so, so this is just, taking a scalar with respect to a vector will result in another vector of the same dimensions, and that's what we have. So I'm going to take this, I'm going to just replace the partial of Zn3 with respect to An2 is going to be replaced with W2 transpose. So I'm going to just take this value right here and plug that in right up there, okay? And so, so that's what I have here, okay? So I've just replaced this with W2 transpose, and now I still need to get the partial of An with respect to W1, okay? So at this point, if we think about what A2 is for observation n, okay? Can I open up the same thing here? So A is what happens after we pass Z through the activation functions. And so for one observation, we're going to have 3 values in A. So A is currently a 1 by 3 vector, okay, for observation n. And it is the result of passing Z through the activation function, element-wise. Okay, we just apply the activation function f element-wise to what Z is. So Z will have the same dimensions as A, okay? And so the partial of A with respect to Z is going to be f prime of Zn2, okay? And so I'm going to take this and I'm going to plug that into here. So the back propagation is kind of the idea of, you take the previous result and you just keep multiplying things so that whatever change happened up here, continues to propagate backwards as you work backwards through the network, okay? And so, we're just working with partial derivatives, and, we split the partial derivative an with respect to W1 into, with respect to Zn, and Zn with respect to W1. Okay, and so, so I'm going to replace this with f prime of Zn2, okay? So this is where we are now. And now we need the partial of Zn with respect to W1, okay? So we have Zn2 with respect to W1. And so, again, if we look at our matrix, Zn, when I pass in one observation, which is 1 row, 2 columns, and I multiply it by our W matrix, which is 2 by 3, I'm going to get a 1 by 3 matrix here, okay? So Z is 1 by 3. Our input, for one observation is 1 by 2, and we're multiplying it by a 2 by 3 matrix, okay? And so what we're asking for is what is the partial derivative of Z, which is 1 by 3, with respect to a matrix which is 2 by 3, okay? And so, so it's weird, right? You have a vector output, a 1 by 2 vector output, and and you want the derivative of that thing with respect to a 2 by 3 matrix. And I tried to look up like a direct article on this, and I couldn't find much on the internet, and all I could find was this cursed question on whatever, Stack Exchange or whatever it is. Okay, it had just like questions that were like upvoted and downvoted, and people saying this is right and wrong and things like that. It's almost I don't know. Do you guys remember the Jacobian? Okay, so the Jacobian is you've got a vector output and a vector input, and if you take the partial of the vector with respect to the vector, you get a matrix. Okay, but now it's almost like the kind of the opposite, and you have a vector output with a matrix, and so the partial of this vector output with respect to the matrix is going to be a vector. Okay, so when we take the partial of z with respect to w, we're going to get a vector that's 1 by 2. Okay, because in order for this to line up, you know, if you're going to something multiplied by a 2 by 3 to make a 1 by 3 has to be a 1 by 2. Okay, so if I take the partial of zn with respect to w1, it's going to result in a 1 by 2 vector matrix. Okay, and you know, if we pay attention to kind of just the matrix multiplication that's happening between x and w, I think the partial derivative can be taken without too much pain. Okay, so this is basically what's happening. If we write out every element in x, x of n, one observation in x, multiplied by our w matrix, okay, our 2 by 3 w matrix. And so this is what we have. And so I probably should have colored these row-wise rather than column-wise. Basically, you know, I take xn1, multiply it by w11, and xn2, and multiply it by w21, okay? And I do, you know, this times this produces the middle value, and this times the last column produces the third value. So zn is a 1 by 3, this is 1 by 2, this is 2 by 3, okay? And so if we just kind of take the idea of the, I don't know, our coarse definition of a derivative or gradient, in, like in a numeric derivative, or numeric gradient, if you just take, if we go through here and we just perturb, or we just add a tiny little epsilon to this, and we see how much does it change z, okay, we can see that if I add a tiny bit of epsilon to this, okay, to any value on the top row, it's going to alter z by x1 times epsilon, right? So if I add a tiny epsilon to w11, the amount it's going to change is going to change by xn1 times that epsilon. Okay, if I add a tiny bit to w12, it's going to change by xn times w12, because that's the only thing being multiplied by w12. Or if I change w13 by xn1, it's going to alter, by epsilon, it's going to alter it by xn1, okay? And so we can see any value that anything we change in the top row is going to be altered by xn1, and likewise, if I change anything in the lower row, it's going to change by xn2. And so the derivative of this, or the gradient or partial derivative of zn with respect to w1 just ends up being a 2 by 1 matrix, which is going to be the transpose of x of n. Okay, so we take x of n and transpose it, and that's going to be the gradient of zn2 with respect to w1. Okay, so this is what we have, and I plug that in, and this is kind of what we have in kind of its current form, and the dimensions don't line up, and so I just have to, we're still talking about just one observation, x of n, and in order to kind of get this to work, I just move this, I rearrange some terms and I move this up here and I do element-wise multiplication between W2 transpose and F prime of Zn, okay? And so, this thing will reduce to a 1 by 3. We've got a 1 by 1, and we can see that if we look at all of these elements here, our result will be a 2 by 3. Okay, we're going to have a 2 by 3 matrix, which is what we want. We want the gradient of J with respect to W1 to be a 2 by 3 matrix, which it is. But this is just for one observation. So I'm going to take our current result and I'm going to try to generalize it for just one observation to all n observations at the same time. So basically I'm going to try to get rid of all of the subscripts here and just say let's deal with the full matrix X, kind of the full vector Y and the full vector Y hat and all of that stuff. And so, so this is it for one observation. And so when I get rid of the subscripts and deal with the full matrix to kind of get rid of the summation sign, all of these things that are 1, 2 by 1 becomes 2 by n. This thing is n by 1. This F prime is n by 1. W transpose remains 1 by 3. This is a weight matrix, so that's not subject to n. And this is n by 3, okay? And so I'm going to kind of group these together to kind of keep our terms likewise together. Earlier we had called, negative of y minus y hat element-wise multiplication with f prime of z. Oh, I'm sorry. I need to get rid of the subscript here. Sorry, slide 13. I need to make a correction there. Okay, it should be this. Okay, and so we call that delta 3. So this just simplifies to delta 3, which is n by 1 right now. And then so just kind of combining these things together, n by 1 times a 1 by 3 is going to end up n by 3. And then, so now I have an n by 3 matrix and an n by 3 matrix, and I can do element-wise multiplication to preserve this as an n by 3 matrix, okay? So in R, element-wise multiplication is just the asterisk. You just take, one matrix, and you take another matrix of the same dimensions, and if you do asterisk, it's going to go element-wise, and it will return another matrix of the same dimension. So this, which is n by 3, multiplied by n by 3, element-wise, will still be n by 3. And then I can do matrix multiplication between X transpose, which is 2 by n, times this thing, which is going to result in a 2 by 3 matrix, which is what we want because we want the gradient of a scalar with respect to the matrix to have the same dimensions as the matrix, okay? So we have 2 by n by 3, which will result in a 2 by 3, and so we have this. Okay, is that okay? And I'm a big proponent of the best way of learning is doing it by yourself, doing it on your own. So you'll have a similar exercise where you have to figure out the gradient with respect to the bias matrix B, okay? Which it'll be tough, but I think you can do it, okay? Help each other out, right? Okay, so now all that's left is to code everything up, okay? Turning all of this math into code is actually the easiest part of all of this. Like, the math is the hardest, and then turning it into code is not so bad, okay? So anyway, first I define a function sigmoid, okay, which is just taking exactly what we have here. This is our sigmoid function, and I make it a function here. It takes something here, and all of these are vectorized, so you can put a matrix into Z here, and it will return a matrix of the same dimensions, so no problem, okay? I think I don't know where the example I used. So I'm just following the exact same example, whoops, from the Welch Labs videos, which I don't know if this is the wrong one. Okay, that was our colorful lecture. Okay, so I think these were the example values we had in the Welch Labs video. So so here we are. We put it into the thing. Just so everything kind of works out, we're going to just scale everything so it's down between 0 and 1. I could have taken y and divided it by the max of y, but I think because y has technically test scores can go from 0 to 100, it makes sense to kind of divide everything by 100. And this is just so that because the output of the sigmoid function goes from 0 to 1, so it makes sense that we align our observed values to be on the same scale. Okay, so this is just scaling everything. And then here I write input layer size, output layer size, and hidden layer size. I leave these as variables in case I want to be flexible later. Okay, right now I've got 2 inputs x. My hidden layer has 3 nodes in the hidden layer, and then our output has 1 node. Okay, but we can by leaving these as variables, I can flexibly change my network. And then again, this is the math part for the forward feed. We did x times w is z. We apply the activation function to f and we get a. A times w is z, and we apply the activation function f to that and we get y hat. Okay? So for forward feed, I just defined some matrices w1 and w2. Okay, just like we have here, w1 and w2. And w1 is 2 by 3 and w2 is 3 by 1. Okay? And then so I do x times w to get z2, just like we have here. X times w1 is z2. And then we apply the sigmoid activation function to z2 to get a2, which is what I have here. Sigmoid of z2 is a2. Then I take a2 and I multiply it by w2 to get z3. a2 times w2 is z3. And then I apply the sigmoid onto z3 to get y hat. Okay? So all I've done is just exactly what I've done in the math. All right? And these are all these are matrix multiplications, so I have to use the, whatever you call this thing, percent star percent. Okay? So that's forward feed. That's right. All we did was turn this directly into code. This is not too crazy. Okay? We define our cost function. We take in kind of basically a vector y and another vector y hat, which we've produced here. And then we're just going to take the difference, we square those, and we sum them up, and we multiply it by 0.5, just so everything kind of aligns. And then so if I just currently throw in our 3 observations, y and y hat, it actually spits out a value. And then we need to figure out what our gradients are. So to get our gradient, we've got, I write a function for sigmoid prime, which is on an earlier slide somewhere, and it's e to the negative z, 1 plus this. So this is just directly from what we found in the math. Okay? And then now, we code up our gradients. Okay, so earlier we established that the gradient is this, A2 transpose times minus y hat, element y's multiplication with f prime of z3, okay? And so if we call this thing delta 3, okay, it's exactly what this is, right? Minus y hat with element y's multiplication of f prime, which is sigmoid prime of z3. Okay, so this is what we have here. And then our gradient, gj, with respect to j with respect to w2, which we have dj dw2, is a2 transpose, which is what I have here, a2 transpose, with matrix multiplication times delta 3, which is what I've got here. Okay, so I've just directly gone from my math to a line in code. Okay, and this is all like coded in an R Markdown document. So this, when I write this, this is actually being performed by the computer, okay? And then for the other gradient, we have J with respect to W1 is X transpose times all of this. And so we defined delta 2 as all of this over here, which is delta 3 multiplied by W2 transpose, okay? And so we have matrix multiplication there. Element-wise multiplication with F prime, sigmoid prime of Z2, okay? So I've just taken this and I've coded that right here. And then this with respect to W1, J with respect to W1 is X transpose times delta 2. So I do that. Okay, so again, just taking exactly the math part and putting it into code. Okay. All right, and now that we have the gradients, we can do what we wanted to do from the beginning, which is apply gradient descent, which is just going to iteratively work through all of this stuff. Okay. So to kind of start off, I'm going to just start define my W1 and W2 matrices. I guess I should have not written hard code 6 and 3, but I'm just using some random weights for W1 and W2 matrix. And then I create a kind of a matrix called cost history. Or not a matrix, a vector, to just so I can see how our cost function improves. And then the scalar, this is like our gamma or this is basically the gamma that we're using for our gradient descent, okay? You can play around with this. It turned out a big value like 5 worked for me. So I'm gonna do 10,000 iterations of this thing. And then this is the gradient descent, which it looks like a wall of code, but it's, I don't think it's all that terrible, okay? Of course not, but, so basically this part takes your current weights of W1 and W2, does the forward feed, okay? Taking in your X and just moving them forward, okay, to get your Y hat. And we need to do that in order to calculate the value of our current cost function, okay? Which I guess technically this is not required for gradient descent, okay? For gradient descent, you don't actually need to keep track of the cost function, but I wanted to do that. So so I do this and I calculate the cost between Y and Y hat, and I'm going to store this in my cost history vector, just so I can kind of keep track of how the cost function is performing, okay? And then, and these are the basically the 4 lines of code that calculate the gradient, okay? So this is exactly what I had earlier, where I calculate dj, dj with respect to W2 and dj with respect to W1, okay? So this calculates the gradient, and this is based on all of that back propagation calculus work that we had to do, basically just turns into this, okay? And this is the only part that's really the gradient descent algorithm, okay? It's take your current values and you subtract off, the scalar gamma multiplied by your gradient, and then you take your current values of W2 and you subtract off the scalar multiplied by your current gradient there, okay? Which is gradient descent, right? You take your current location and then you just subtract off something, okay? Take a step in the direction opposite of the gradient, okay? And then so really, these lines of code are all that's necessary. I threw this in here so I can just keep track of the history of the cost. Okay, and then so I let this run, and these are the results for the W1 and W2 matrices. These are basically uninterpretable. Okay, I have no idea what this stuff means, okay? It's technically the weight between input 1 and node 1, 2, and 3 in our hidden layer, but I don't know what nodes 1, 2, and 3 even symbolize, okay? So there's not much interpretation here. But we can compare the results of what our neural network predicts for our 3 observations and the 3 actual values, okay? So the 3 actual values were 75, 82, and 93, and after training it, my neural network will predict basically 75, 82, and 93, okay? Which I would consider a success. Let me, and I forgot to plot the cost history function, okay? And so, so this is what we have, and okay, so I've got cost history. Let me just show you a plot of that. So. Okay, and so this is what our cost history looks like. The cost function started off high at 0.01, and in the beginning it took dramatic steps to reduce it, and then the gradient got stuck in kind of this flat-ish territory, okay, and then it kind of came across like some breakthrough somewhere, and it took a slope, and then again it kind of flattened out. This is we could have stopped here or anywhere along this flat region, and our prediction results would probably be quite similar. We're getting like hardly any improvement. If we take a look at the log of the cost history, then we can see we're getting logarithmically like it improves. So it drops dramatically, and here this constant thing here just means we're the fact that the slope of the log is constant. It means I'm kind of just incrementally improving, like I'm reducing my error by like 2% each time, okay? So there's just kind of this constant improvement, but when your error is quite small, reducing it by 2% produces, you get these kind of diminishing returns. But if you look at it, logarithmically, it says, you're still improving, so on and so forth. Let's see. Okay. After the midterm, we'll, I think, do a fun, I don't know how fun, we'll just take this same neural network, okay? I guess, I don't know if you're impressed by this at all, but these are just matrix operations, okay? It's not like I'm using some mystery package. Like, if you were to implement a neural network in R, full disclaimer, you're not going to do it this way, okay? You're going to use like neural net or NNet or some of these prepackaged versions in R. But we've also achieved basically the thing that we wanted to do just using simple matrix operations, okay? It took us a lot of math and calculus to kind of get to this point, but once we got through that, it's just a few matrix operations, and we're applying gradient descent here. And so we're gonna basically take this same structure and apply it to this MNIST handwritten digits data set, which many of you might be familiar with, maybe not. It's kind of like the first taste of image recognition, but it's like super clean data, and it's very nice to work with, whereas real life is like way worse and complicated. But we have this nice thing where we're going to feed it these little images, and it's going to tell me what number it sees. And again, we're just going to use basically this kind of neural network setup, and and I think it'll be good. But that will be Friday. I guess the lecture after the midterm exam. So we'll end here for today, and good luck as you guys study for the midterm. We'll see you then. I will send out a seating chart. Just keep your eyes open for that. Okay.